Hi, welcome to Physics Teacher, the channel that prepares you for the Waterloo Math and Science Contest. This is a high school Sir Isaac Newton physics contest question, and in it we have a pilot flying a vertical loop at a constant speed, drops her sandwich right at the top of the arc. It falls 1 centimeters in 0.2 seconds relative to the plane. She recovers the sandwich, eats 20% of its mass, and then flies another arc. Again, releasing the sandwich at the top just as before, maintaining the same radius. But this time, the sandwich moves up at 5 centimeters in 0.33 seconds. For this to happen, the speed of the plane must have been different. So the question is to calculate the ratio of these speeds. Give it a try, and I'll be right back with the solution. So this question is a mixture between relative motion and centripetal acceleration. So let's start by looking at 3 frames of reference and labeling them. Let's call S to be our sandwich. We will call P to be the plane. And we will call E to be the Earth, or the ground frame. Now also, since the plane is at the top of this arc and centripetal acceleration will be down, to simplify things in this problem, I'm going to label down to be our positive direction. Now when we drop the sandwich during the first arc, we see that it falls 1 centimeter in 0.2 seconds. Now this says relative to the plane. So let's look at these relative accelerations. So first we're going to have the acceleration of the sandwich relative to the plane, and that is going to equal the acceleration of the sandwich relative to the Earth. And using the chain rule, we can add the acceleration of the Earth relative to the plane. Now this doesn't make too sense. What's the acceleration of the Earth relative to the plane? So let's switch that, and instead we are going to reverse it and change the sign to a negative. So we'll have it subtract the acceleration of the plane relative to the Earth. So here's our relative motion equations for acceleration. Now we can go ahead and calculate the acceleration of the sandwich relative to the plane using the information that is given. Now assuming in both cases, since it is dropped, we're going to assume the initial velocity is 0. So we can use our motion equation, which says our vertical displacement is equal to the initial velocity in y times time plus 1/2 times acceleration times time squared. So again, we're going to set initial velocity to 0 since it's being dropped. And we're going to rearrange this to solve for acceleration. So acceleration is going to be 2 times the displacement in y divided by time squared. So in the first drop, we have 2 times our displacement is 1 centimeter. Let's put that into meters. So 0.01 meters divided by the time squared, which is 0.2 seconds, all squared. And that gives us an acceleration of 0.5 meters per second squared, and it's positive, so it is down. Now this is the first sandwich, and it is going to be the acceleration of the sandwich relative to the plane, since our pilot is in the plane and making the observations from that frame of reference. Now let's also calculate what the acceleration would be for the sandwich during the second drop. So same equation, right? We rearrange it the same way, but for the second drop, so this is first drop. For the second drop, where we have 5 centimeters in 0.33 seconds, we will have A equals to, rearrange it the same way, 2 delta dy over time squared. And that is going to equal 2 delta dy is 5 centimeters. Put it into meters, but also realize that it's up. And so according to our coordinate system, that's going to be negative. So minus 0.05 meters over our time, which is 0.33 seconds, and we will square that. When we do that, we get an acceleration of minus 0.92 meters per second squared down. So that is the acceleration of the sandwich relative to the plane for our second drop. So now what I'm going to do is let's analyze the first drop using our relative motion equation for the accelerations. Now the acceleration of the sandwich relative to the plane for the first drop is 0.5 meters per second squared. The acceleration of the sandwich relative to the Earth, now you have to realize the sandwich is just in free fall, right, when you drop it. So relative to the Earth, it's going to accelerate down at 9.8 meters per second squared. And then we subtract the acceleration of the plane relative to the Earth. So the plane is undergoing centripetal acceleration, and our equation for centripetal acceleration is v squared over r. So I'm going to subtract v, let's call this v1 squared over r for the first drop. And this I'm going to call equation 1. Now let's do the exact same thing, but we're going to do it for the second drop. So for the second drop, we have minus 0.92 meters per second squared equals, again, sandwich relative to the Earth is just in free fall, so that's 9.8 meters per second squared. And then we're going to subtract our centripetal acceleration for the plane, which we'll call v2 since the speed is changing, squared over r. And we'll call this equation 2. Now each equation I am going to rearrange to solve for our v squared over r term. So in equation 1, we will have v1 squared over r is going to equal to 9.8 minus 0.5, which is just 9.3 meters per second squared. Now the second equation, we're going to do the same thing. So we're going to get v2 squared over r is going to equal to 9.8 meters per second squared plus 0.92 meters per second squared, which is going to give us 10.72 meters per second squared. Now if I take equation 1 and divide by equation 2, we will get v1 over v2 all squared. And then if I take the square root of both sides, we'll get v1 over v2 equals the square root of 9.3 divided by 10.72. And when we calculate that, we get 0.93. So our answer is D.